Swayam Prabha. Digital India. Educated India.
In this class, we will talk about or give you an overview of automatic flight control systems. They are of three different categories. One is called stability augmentation systems. So, in case your aircraft does not possess the required stability characteristic as per the requirement of flying and handling qualities, then you have to artificially augment the stability of the aircraft using what is stability augmentation system. So, what you are trying to do here is you are trying to use a feedback control mechanism, wherein the objective is to try to change the dynamic characteristics of aircraft. For example, let us say your short period response in angle of attack looks something like this. Now, from here we can read what is the frequency of the response and the damping. And these are natural response. So, the aircraft without control systems, bare design results in giving us these numbers. Let us say these numbers are not satisfactory. In such a case, we can use these stability augmentation system to change the frequency and the damping characteristics of the aircraft using a feedback mechanism. The other type is called control augmentation system. So, in case you are still not able to, this is stability augmentation system is only to change the dynamic response of the aircraft. Here control augmentation system is basically to either to enhance the dynamic response beyond what is possible by using stability augmentation systems, or you could have some control objectives that need to be satisfied, and there you want to design a control system which can meet the objectives. some other control objectives. The third one is what we will talk little more in detail, is autopilot systems. Autopilot systems are mainly used to keep the aircraft on a prescribed path or attitude. So, what we want to do here is design a control system such that for example, this height is maintained throughout constant in flight in cruise. So, here the autopilot engaged with this constant altitude condition is called altitude hold autopilot. So, the idea is to design control systems which will meet these objectives, but not really bothering about how the dynamic response is looking like. Of course, the control systems that we have to engage to maintain the altitude should not result in unwanted situation, unwanted transient response. So, these autopilots are also including some features which will try to control the dynamic response. So, let us look at some of the autopilots that are normally seen on an aircraft. Pitch, attitude, hold, autopilot. Altitude, hold, autopilot. Mach, hold. Autopilot, roll, attitude, these are some of the autopilots that an aircraft has on board, and automatic landing systems. So, what we are trying to do here is we are trying to give some comfort to the pilot. Pilot does not have to keep holding the stick to maintain, for example, the altitude in case of a cruise level flight, or a bank angle in case of a sustained steady level turn. So, we will look at each one of them in some detail, not exactly giving the complete detail. the idea actually can be represented using this schematic, which is also called a block diagram. So, this is about controlling the pitch angle, theta is the pitch angle here. So, this is a reference theta at which we want to keep the aircraft at all time, even in the presence of disturbance. So, what is happening here is as soon as there is a change in pitch angle from this reference condition, the attitude gyro which is fixed at this condition will be reading an error in change in pitch angle, and that error is going to actuate elevator in such a fashion that this theta reference minus theta is minimized. So, this theta is being read using this attitude gyro and is being fed here, is comparing the theta with this theta reference, and if it is not 0, then there is an error which is being introduced here. This error proportional to that error, this elevator is being deflected, and that in turn is giving theta, which will try to minimize this error in pitch angle. So, pitch angle actually is, when we talk about controlling the pitch angle, we are actually not controlling the flight path angle or the angle of attack independently. So, gamma here is flight path angle and alpha is angle of attack. So, let us say we are flying a level condition. Actually, this autopilot is engaged in a wing level condition. So, if we look at the equation of motion of equilibrium, lift is equal to weight So, whenever there is a change in throttle, that changes the velocity, and if this change is to increase throttle somehow, then the alpha goes down to balance this equilibrium, and when alpha goes down, what happens is gamma has to go up. So, what happens, because we are trying to maintain the pitch at the reference condition, such a thing can happen. Even when we are flying a climb flight, it may so happen that finally, if we are just using this controller autopilot, finally the aircraft may just level out. So, this is not a very popular autopilot, but is used within another autopilot, for example, this altitude hold autopilot. And the other disadvantage of this is that if we just look at this kind of feedback mechanism, it is not really controlling the dynamic response. So, no better attitude pitch attitude hold autopilot will look so this is a compensator. This is what we are talking about. Compensator is used for augmenting the control power of the aircraft. It's almost acting like a control augmentation system. So, there is a inner loop which tries to change the dynamic response or damping actually in such an autopilot. So, this kind of arrangement not only meets the criteria of keeping the pitch angle at constant, but also tries to change the dynamic response using this inner loop. So, this is the inner loop which is using the pitch rate feedback through this rate gyro, and this results in a better short period damping. Clearly, as the name suggests, the main function of this autopilot altitude hold autopilot is to maintain an altitude, a prescribed altitude, which is called H reference here. Idea is same. So, you have to read the actual altitude, compare it with the reference altitude, and proportional to the error that is introduced in the altitude, deflect controls so that you can reduce this error. So, typical element of the altitude hold autopilot control systems are these. Now, this delta E is a modified delta E which is going into the aircraft dynamic equations, and that is outputting this H. As soon as this H becomes H reference, this control system may stop functioning. The altitude sensor is based on the pressure reading. So, the altitude that we are measuring here is the pressure altitude. An altitude hold autopilot actually holds aircraft within 200 feet of the H, which is reference H reference altitude. So, it keeps the aircraft within this plus minus 200 feet, and actually it starts signaling, starts giving a warning signal. As soon as altitude from reference changes by plus minus 100 feet. So, we can clearly see that 200 feet is actually not a small number, but a typical altitude hold autopilot can be engaged to give this kind of performance. The main function of Mach or velocity hold autopilot is to keep the velocity or Mach at constant value in climb or ascent phase. And so, velocity has to be maintained constant at the prescribed value. This again uses a elevator feedback. So, we feed the variable which is Mach number here or the velocity to the elevator, and elevator has to act appropriately to keep the velocity constant. But if we are flying a cruise level flight, in order to maintain speed in this particular flight, we also need to use throttle. So, use of throttle and elevator both together is mandatory. Let us look at the block diagram of a Mach hold autopilot. So, it is similar to what we have drawn earlier. So, you have to remember that each of these autopilots are for a specific purposes. So, if we are trying to hold the velocity here, it can only hold velocity and it is not going to do anything else. So, if you want to do something else also, for example, controlling the dynamic response, then we can have something within the loop of this control system. So, the main outer loop will try to control the Mach number or the speed, and the inner loop can be used to change the dynamic response. So, this one here is using the throttle to keep the velocity constant. A feedback element can be, for example, a sensor which can read the actual speed. So, in general, basic feature is to basic feature of any control system will using feedback will look something like this. Automatic landing systems. So, landing is usually a difficult maneuver because many times the visibility near the ground may be poor, or the weather condition can be poor or bad. So, what may just happen is when an aircraft is approaching the runway or it's about to go on to a landing approach, it may just find itself slightly disoriented from the center line of the runway, and there could be presence of wind also which can move it laterally. So, the aircraft if it is not having an autopilot kind of systems, landing system, in such a case aircraft is guided by a beam. Beam provides beam which is a radio beam. This beam provides information regarding the reference trajectory, and the aircraft is supposed to follow the beam. So, the mechanism this instrument equipment which radiates this beam is at right at the touchdown point. So, this equipment which or the station from where the beam is thrown is this beam is okay. So, an aircraft which may be following, let us say, this glide path, this is called. So, this let us say this aircraft is following this path, not really a glide path, and it is supposed to follow this beam. So, this is actually the glide path, and this station is at touchdown point, and after which the aircraft has to flare out and then move on the landing, move on the runway for some distance to before it stops. So, this is called flaring. So, automatic landing system will consist of guiding the aircraft to this glide path and to flare when it is coming closer to the touchdown point, so that it can land safely. So, this angle is the reference flight path angle, gamma is the flight path angle. So, let us say this is the point where the aircraft is at any time t1, and afterwards after time t2 it has after some time at time t2 it has moved to this point, but it is supposed to touch down here. So, the amount by which is deviating from its required glide path can be denoted by these angles. So, this delta is the deviation angle, r is the distance which is called range, and this is the lateral correction. So, this d is the deviation from the glide path. An aircraft is having some velocity V a on approach. So, clearly both these angles are negative because I am trying to land the aircraft. So, glide path deviation this d is given by r into sin delta. This angle is usually small. So, even though the picture is looking big here, this angle is small. So, that this d is r into delta. D dot in order to correct the glide path, there is one on approach path actual, and this is what it should, this is the reference glide path and this is the actual glide path. So, a correction has to be done for changing this d. So, d dot is sine of now dt at any time can be obtained by integrating this equation. Star. Okay, so with this background, let us look at how actually an automatic landing system looks like. So, here we are again looking at the autopilot for automatic landing. The reference variable here is the deviation angle, which has to be 0. Error in delta, the deviation angle is fed to what is called glide path coupler, which is trying to change the attitude of the aircraft, so that it is following the glide path. And here an attitude hold autopilot is engaged because theta can be maintained at the prescribed value. This will change the flight path angle according to this dynamics. This gives gamma. V a into gamma is actually resulting in the, so if you look at the altitude, rate of change of altitude is V A sin gamma. So, or rate of, is also called rate of climb or rate of descent. And this gives this deviation from the glide path, which multiplied by 1 over r gives delta, actual delta. And this will be fed back to compare it with the reference condition. So, the objective of this is to control this deviation angle. The flare control is having another control block in place along with it, so that when a craft is coming closer to this point, the touchdown point, it has to flare out and roll out. So, there is a separate control system which gives automatic flare. So, with this we conclude our lectures on flight dynamics. This is